In describing mixture composition, let us consider a closed system consisting of a gaseous mixture of two or more components. The composition of the mixture can be described by giving the mass or the number of moles of each component present. The mass, the number of moles, and the molecular weight of a component I are related by this equation. N sub I is equal to lowercase m sub I over the uppercase m sub I, where the m sub I or the lowercase m sub I is the mass, n sub I is the number of moles, and the uppercase m sub I is the molecular weight of a component I respectively. When the lowercase m sub I is expressed in terms of the kilogram, n sub I is in kmol. With the lowercase m sub I is in terms of the pound mass, then the n sub I is in pound mole. However, any unit of mass can be used in this relationship. Moreover, the total mass of mixture M, lowercase m, is the sum of masses of its components as shown in the equation 12.2. On the other hand, mass fractions. The relative amounts of components present in the mixture can be specified in terms of mass fractions. The mass fraction, or the MFI of component I, is defined as this. Next is the gravimetric analysis. A listing of the mass fractions of components of a mixture is sometimes referred to as a gravimetric analysis. That is, the sum of the mass fractions of all components in a mixture is equal to the unity. Moreover, the total number of moles in a mixture, N, is the sum of the number of moles of each of its components, as shown in the equation 12.5. Next is mole fraction. The relative amounts of the component present in the mixture also can be described in terms of mole fractions. The mole fraction, Y sub I, of component I is defined as Y sub I is equal to the N, lowercase n sub I, over N. Next is volumetric analysis. An analysis of a mixture in terms of mole fraction is called volumetric analysis. That is, the sum of mole fractions of all components in a mixture is equal to unity. The next is molecular weight. The apparent or average molecular weight of a mixture, uppercase M, is defined as the ratio of the total mass of the mixture, lowercase m, to the total number of moles of mixture, N. That is the equation. Or it can be written and can be transformed in alternative form as this one. In converting mass fractions to mole fractions, we have this example. A gas mixture has the following composition in terms of mass fractions: hydrogen gas or H2 0.10, nitrogen gas 0.60, carbon dioxide 0.30. We're going to determine the composition in terms of mole fractions and the apparent molecular weight of the mixture. In solving this, we have a known value, which is the gravimetric analysis of a gas mixture. Next is we're going to determine the analysis of the mixture in terms of mole fractions or molar analysis and the apparent molecular weight of the mixture. In solving this, we have come up with this analysis. So we're going to use the equations 12.1, 12.3, and 12.6 because these are the key relations required to determine the compositions in terms of mole fractions. We're going to use these equations. Although the actual amount of mixture is not known, the calculation can be based on any convenient amount. Let us base the solution on 100 kg. Then with equation 12.3, the amount of the lowercase m sub I of each component present in kilogram is equal to the mass fraction multiplied by 100 kg. The values are listed in column 2 of the accompanying table. Column 3, on the other hand, of the tables gives the respective molecular weights of the components. Column 4 of the table gives the amount of the n sub I of each component in kmol per 100 kg of mixture obtained using the equation 12.1. The values of column 4 are obtained by dividing each value of column 2 by corresponding the value of column 3. The sum of the values of column 4 is the total amount of mixture in kmol per 100 kg of mixture. And finally, using the equation 12.6, column 5 gives the mole fractions as a percentage. The values of column 5 are obtained by dividing the values of column 4 by the column 4 total and multiplying by 100. So we get the answer for this in a percentage form. The next is we're going to use to find the molecular weight. So the apparent molecular weight of the mixture can be found using the equation 12.9. So the calculated mole fractions, the value can be determined alternatively by using the column 4, total giving total amount of mixture in kmol per 100 kg of mixture. Thus, with equation 12.8, we can get this answer, 12.79 pound per pound mole.
Dalton's law states that the pressure of a mixture of gases is equal to the partial pressure of the individual component gases. The partial pressure is the pressure that each gas would exert if it alone occupied the volume of the same temperature. Let's say we have a container with 3 different gases, gas 1, gas 2, and gas 3. Note that all gases are inside the same container. This means they all have the same volume. Now, let's take the same container and spread the gases out equally while holding the volume constantly each container. The sum of the partial pressure of the 3 gases will equal to the total pressure of the mixture of gases. And now let's look at the pressure meter above the gas chamber to know that each partial pressure from the individual gases equals to the pressure of all the gases in the same container. Now let's look at the formula for Dalton's law of partial pressure. But first, let's arrive the ideal gas law where pressure times volume is equal to nRT. We can see that the pressure is equal to nRT over V. Now let's look at the Dalton's law of partial pressure, where at a constant volume we can add the partial pressure volume of the individual gases to equal the total pressure of the combined gases. Amagat's law describes the behavior and properties of mixture of ideal gas as well as some cases of non-ideal gases. It is used in chemistry and thermodynamics. It also states that the extensive volume V is equal to NV of a gas mixture is equal to sum of volume VI of the K component gases if the temperature T and the pressure P remains the same. According to Amagat's law of partial volume, the total volume of a non-reacting mixture of gases at constant temperature and pressure should be equal to the sum of the individual partial volumes of the constituent gases. So if V1, V2, V3, and V are considered to be the partial volumes of the components in the gaseous mixture, then the total volume V would be our respondent represented as V is equal to V1 plus V2 plus V3 plus Vn is equal to summation of V.
Evaluating the internal energy, enthalpy, and specific heats are needed to apply the conservation of energy principle to a system that involves ideal gas mixture. Furthermore, entropy of a mixture is required in conducting analysis using the second law of thermodynamics. In evaluating internal energy and enthalpy of ideal gases, since they are functions of temperature only, the values of these properties for each component present in the mixture are determined by the mixture alone. So the internal energy and enthalpy for ideal gases can be expressed as, based from these two expressions, we can say that these two properties can be found by adding the contribution of each component at the condition at which the component exists in the mixture. On a molar mass basis, these two equations above can be rewritten as, now, if we divide each component by the total number of moles of mixture, we can obtain the specific internal energy and enthalpy of the mixture per mole of mixture, and these two properties can be expressed as, now, the specific heats at constant volume and constant pressure can be obtained by differentiating the specific internal energy and enthalpy respectively, giving us these expressions for the specific heats of the mixture on a molar mass basis. So entropy of an ideal gas depends not only on temperature but also with partial pressure, and the evaluation of the entropy of a mixture has the same way in evaluating the internal energy and enthalpy, and that gives us the expression. Now, on a molar mass basis, the above expression can be rewritten as dividing this by the total number of moles of mixture gives us an expression for the entropy of the mixture per mole of mixture. On a mass basis, the specific internal energy, enthalpy, and entropy are evaluated on a unit mass basis. So this table shows how to evaluate properties on a mass basis for binary ideal gas mixtures. The mixture enthalpy, internal energy, and specific heats are still functions of temperature, and the mixture entropy is still a function of temperature and partial pressure. So mole fraction in molar basis is replaced by mass fraction of component I in mixture entropy.
Analyzing system involving mixtures to perform thermodynamics analysis of system involving non-reacting ideal gas mixture requires no new fundamental principle. So, the conservation of mass and energy principle and the second law of thermodynamics are applicable in the forms previously introduced. So, the only new aspect is the proper evaluation of the required property data for the mixture involved. So, here is the given example. A mixture of 0.3 pounds of carbon dioxide and 0.2 pounds of nitrogen is compressed from 1 atmospheric pressure with the initial temperature of 540 degree radians to 3 atmospheric pressure and polytropic process for which N is equal to 1.25. So we will be going to determine the final temperature with the unit of degree radians and the work with the unit of BTU, and the heat transfer and the change of entropy of the mixture. So, in solution, we know that a mixture of 0.3 pounds of carbon dioxide and 0.2 of nitrogen is compressed in a polytropic process, which is equal to 1.25 with the initial state of 1.1 atmospheric pressure with the initial temperature of 540 degree, and the final state is equal to 3.3 atmospheric pressure. With the analysis for an ideal gas, the temperature and pressure at the end state of a polytropic process are related by this equation. T2, which is the final temperature, is equal to the initial temperature times the final pressure over the initial pressure raised to the exponent of n minus 1 times n, which is the polytropic process. So, inserting the values, T2 is equal to 540, which is the initial temperature, over the 3/1 atmospheric pressure raised to the exponent of 0.2. Therefore, we can conclude that the final temperature is equal to 673 degree radians. So, in finding the work of the compression process is given by work is equal to the integration of 2 and 1 with a p derivative v. So, introducing PV raised to the exponent of n is equals to constant and performing the integration. So, we arrived in this equation. Work is equal to the final pressure times the V squared minus P1 minus P1 times V1 over 1 minus n, which is the polytropic process. So, with the ideal gas equation of this state, this reduces the equation below. So, the mass of the mixture is, we know that 0.3 plus 0.2 is equal to 0.5 pounds. So, the apparent molecular weight of the mixture can be calculated using the M is equal to M minus N, where N is the total number of moles of mixture. So, the numbers of moles of carbon dioxide and nitrogen are respectively. So, as you can see, the total number of moles of mixture and carbon dioxide, 0.3 over 44, we arrived at 0.0068 pounds per mole. So that is the total number of mole mixture and carbon dioxide. And the total number of moles of mixture and nitrogen is equal to 0.0071 pounds per mole. So the total number of moles of mixture, and we can conclude that the apparent molecular weight of the mixture is equal to 35.97. So now we will calculate the work. So work, as you can see, we will substitute all the given values And we finally arrived at work is equal to negative 14.69 BTU. So where the minus sign or the negative sign indicates that work is done on the mixture as expected. So with the assumption, the closed system energy balance can be placed in the form of heat is equal to change of internal energy of the mixture plus the work. So since we have the value of work, we will find the value of the internal energy of the mixture. So the change in the internal energy of the mixture equals to the sum of the internal energy changes of the components. So as you can see in your screen that the change of internal energy, we will input all the given values provided lately. So we will arrive at the given value of the change of internal energy is equal to 11.3 BTU. So since we have all the values we need in finding the heat, so Q is equal to positive 11.3 BTU minus 14.69, which is 14.69 is the work. So we can conclude that the heat is equal to negative 3.39 BTU, where the minus sign or the negative sign signifies a heat transfer from the system. And then the change in entropy of the mixture equals to the sum of the entropy changes of the components. So as you can see in this equation, the change in entropy, so we will substitute all the values given in the previous solution. So the change in entropy in the mixture is equal to 0.068 times the 53.123, which is the value of the total molecular mixture of the carbon dioxide minus 51.0.82 minus 1.986 ln3 over 1, which is the polytropic, plus 0.071. So as per conclusion, we can conclude that the change in entropy is equal to negative 0.0056 BTU over the degree of radiance. So as you can see, the entropy decreases in the process because entropy is transferred from the system, accompanying by the heat transfer.
Psychrometrics is a study of systems involving dry air and water. It is a field of engineering concerned with the physical and thermodynamic properties of gas-vapor mixtures. Since the principles of psychrometry applies to any physical system consisting of gas-vapor mixtures, the most common system of interest is mixture of water vapor and air. Many substances are hygroscopic, usually in proportion to the relative humidity or above a critical relative humidity. Substances include cotton, paper, cellulose, other wood products, sugar, many chemicals, and fertilizers. For air conditioning devices, psychrometric application focuses on its temperature and humidity control, as air undergoes into processing, heating, cooling, dehumidification, and humidification. Cooling towers provide chilled applications in industrial areas or power plants to transfer heat to wet bulb temperatures. Industries that uses these materials are concerned with relative humidity control in production and storage of such materials. Relative humidity is controlled in manufacturer areas where flammable materials are handled. In many industrial applications, it's important to avoid condensation as it causes corrosion on the product.
Humidity ratio or specific humidity is the ratio of water vapor mass to the air parcel's total mass including the dry air and is sometimes referred to as the humidity ratio. The specific humidity is approximately equal to the mixing ratio, which is defined as the ratio of the mass of water vapor in an air parcel to the mass of dry air for the same parcel. Relative humidity, on the other hand, is an air-water mixture and is defined as the ratio of the partial pressure of water vapor in the mixture to the saturated vapor pressure of water at a given temperature. Thus, the relative humidity of air is a function of both water content and temperature. So, the enthalpy of mixing, or heat of mixing or exhaust enthalpy, is the enthalpy liberated or absorbed from a substance upon mixing. When a substance of a compound is combined with any other substance or compound, The enthalpy of mixing is the consequence of the new interaction between the two substances or the compound. So for the entropy of mixing, it is the increase in the total entropy when several initially separate systems of different compositions, each in a thermodynamic state of internal equilibrium, are mixed without chemical reaction by the thermodynamic operation of removal of impermeable partitions between them. So followed by a time for establishment of a new thermodynamic state of internal equilibrium. So for dry bulb temperature, it is the temperature of the moist air as measured by a standard thermometer or other temperature measuring instruments. So when we put this thermometer in the atmospheric air, and what temperature given by the thermometer is called as the dry bulb temperature. So for the wet bulb temperature, it is the temperature of air recorded by the thermometer when its bulb is surrounded by a wet cloth exposed to air. So in the sensing bulb, we will cover the bulb by using a wet cloth, and we put this thermometer to the air, and what able to get at the temperature given by the thermometer is known as wet bulb temperature. So for the dew point temperature, it is the temperature of air recorded by a thermometer when water vapor in the air begins to condense or dew is formed. So when the water vapor in the air starts to condense, then the temperature at which condense has started, it is known as the dew point. And if you record the air with a thermometer, it is known as the dew point temperature.
How to use psychrometric chart. Psychrometric chart is a graphical representation of the physical and thermodynamic properties of air. It is also used to measure the properties of air. For better understanding of psychrometric chart, there are 2 points that should be kept in mind. We need to identify the line, that this line represents which parameter and where is the scale of parameter. The following parameters are seems to be plotted in this chart. First, dry bulb temperature. Second, wet bulb temperature. Third, relative humidity. Fourth, absolute humidity or humidity ratio. Fifth, dew point temperature. Sixth, specific volume. And lastly, enthalpy. In order to use psychrometric chart, we must have 2 parameters. If we have 2 parameters and by the intersection of the 2 parameters, we can find out all other parameters. For example, our dry bulb temperature is 30 degrees centigrade and our wet bulb temperature is 25 degrees centigrade. And we need to find the relative humidity, specific humidity, dew point temperature, specific volume, and enthalpy. So what we have to do is first, we need to draw our first given parameter, which is this one, and our second given parameter, which is this one. Remember that whatever parameters we draw, it should be parallel to the parameter. For example, our wet bulb is 25 degrees centigrade. So these are the lines of wet bulb temperature. So our line would be parallel to the given parameter. Then we find the point of intersection. So this is our point of intersection. What we have to do next is we have to draw a line from the point of intersection to the point of required parameter scale. But our line should be parallel to the required parameter scale because once again, whenever we want to find out a parameter, we need to draw a line parallel to the required parameter line until the scale of required parameter line. For example, relative humidity. So our relative humidity is between 70% humidity line and 60% humidity line. If we draw a line parallel to this line, then if we draw a line here, so our relative humidity is around 68%. Next is specific humidity. Our specific humidity is horizontal, then we draw a horizontal line parallel to these lines. So the scale humidity ratio is between 0.015 and 0.020. So If this is our parallel line, our specific humidity is around 0.18. Next is the dew point temperature line. One point of intersection horizontal to the wet bulb temperature. So this is the line for our dew point temperature, and it is between 20 and 25. So our dew point temperature is around 23.5. For our specific volume, our specific line are this one. So this one, and this one. It is, so we draw a line parallel to this one and this one. So this is now our parallel line. It is between 0.85 and 0.90. But it is near to 0.90, so our specific volume is around 0.88 meter cube per grams. Last is the enthalpy. From the point of intersection, we will draw a line towards the scale. Then our enthalpy is between 60 and 80, but it is very near to 80, so our enthalpy is around 75 joules per grams. So this is how we use our psychrometric chart.
In this video, I am going to explain the process in analyzing air conditioning process, including the mass, energy balance, dehumidification, humidification, and adiabatic mixing of two moist air streams. The purpose of this section is to study the typical air conditioning process using a psychrometric principles. First off is applying the mass and energy balances to air conditioning systems. So we have here, this object is to illustrate the use of conservation of mass and conservation of energy principles in analyzing the systems involving mixtures of dry air and water vapor in which a condensed water phase may be present. So the same basic solution approach that has been used in thermodynamic analysis considered thus far is applicable. So we have here this figure which shows the systems for conditioning moist air. Systems that accomplish air conditioning process such as heating, cooling, humidification, or dehumidification are normally analyzed on a control volume basis. To consider a typical analysis, we can consider this figure. So from the figure, it shows a 2-inlet single exit control volume at steady state, a moist air stream enters at 1, a moist air stream exits at 2, and a water-only stream enters or exits at 3. The water-only stream may be liquid or a vapor. Heat transfer at the rate QCV can occur between the control volume and its surroundings, depending on the application. The value of QCV might be positive, negative, or 0. For mass balance, at steady state, the amount of dry air and water vapor contained within the control volume cannot vary. Therefore, for each component individually, it is necessary for the total incoming and outgoing mass flow rates to be equal. So that is for dry air, that is equal to MA1 equal to MA2. Also for water, that is MV1 plus MW is equal to MV2. So for simplicity, the constant mass flow rate of dry air is denoted by M.A or MA. The mass flow rates of water vapor can be expressed conveniently in terms of humidity ratios, and that is MV1 is equal to W1MA and MV2 is equal to W2MA. With these expressions, the mass balance for water becomes M.W is equal to M.A quantity of W2 minus W1, that is for water. When water is added at 3, W2 is greater than W1. For energy balance, assuming that W.CV is equal to 0 and ignoring all kinetic and potential energy effects, the energy rate balance reduces at a steady state to this one here, the first equation. As we can see, in this equation, the entering and exiting moist air streams are regarded as ideal gas mixtures of dry air and water vapor. So from this previous equation, it can cast into form that is particularly convenient for the analysis of air conditioning systems. First, from the equation, the enthalpies of the entering and exiting water vapor can be evaluated as saturated vapor enthalpies corresponding to the temperatures of T1 and T2 respectively, giving this second equation here, this one. And then, with MV1 is equal to W1MA and MV2 is equal to W2MA, the equation can be expressed as this third equation here. And finally, introducing the equation of 1252, which is from the equation for the water from the previous slide, we come up with this energy rate balance given here. The next one is the dehumidification shown in these figures. The first one is the equipment schematic and the second one is the psychrometric chart representation. When a moist air stream is cooled at constant mixture pressure to temperature below its new point temperature, some condensation of the water vapor initially present will occur. From the figure, it shows the schematic of a dehumidifier using this principle. Moist air enters at state 1 and flows across a cooling coil through which a refrigerant or chilled water circulates. Some of the water vapor initially present in the moist air condenses, and a saturated moist air mixture exits the dehumidifier in section 2 at state 2. Although water condenses at various temperature, the condensed water is assumed to be cooled at T2 before it exits the dehumidifier. Since the moist air leaving the dehumidifier is saturated at a temperature lower than the temperature of the moist air entering, the moist air stream at state 2 might be uncomfortable for direct use in occupied spaces. However, by passing the stream through a following beating section, it can be brought to a condition, the state 3, most occupant would regard as comfortable. For more information, please see the book of Fundamentals of Engineering Thermodynamics 8th edition. It can provide illustrations of the analysis and also applications that can give you information more on the topic. Thank you!